Hey, everybody. Welcome back to another exciting episode of the Hazmat Guys.
Yeah, we are here. And since my retirement, I've had plenty of times on my hands to sit and actually attend webinars that come through my email. And I attended the RedWave webinar about a month and a half ago. Really cool product. So we reached out to them to see if we could get them to talk a little bit more about what they got and what they got going on. And they sent us somebody, which is
we got
unusual,
the guy.
because usually they just hang up on us.
Yeah, we got the doc. So please take a second to introduce yourself.
Sure. I'm John Seelenbinder. I'm the director of product development here at RedWave Technology. I'm kind of in charge of getting the products through engineering, through all the R&D, and then out to the customers. As they said, I'm a PhD in chemistry. I've been working in the portable FTIR world and the hazmat world for about 20 years now. In fact, I started with Smith's Detection in 2003, so it's 20 years almost to the day. So,
and the technology that you guys have out, they are the FTIR, the ones that are hitting the market.
We are using FTIR, and we've expanded what we can do with it. So now we're able to measure gases as well as solids and liquids, and that's where all of the kind of new stuff is coming recently.
And that's where the whole adaptive atmospheric correction things come into play, right?
Right. Okay. So like with gases, you've got a big problem with water and carbon dioxide, which is just in the atmosphere, right? And, it really comes down to like concentration. So if it's like, say it's about 75 degrees, 80% relative humidity, nice summer day, you're talking like about 2% water vapor in there. And we want to measure toxins like in the ppm range. So you've got this huge difference. Carbon dioxide is going to be like 400, 700 ppm, something like that, depending on whether you're inside or outside. And those are just really big concentrations compared to what we're trying to measure. So what we had to do is we had to come up with a new way to take care of that, to compensate for the atmosphere. And that's what we call the adaptive atmospheric compensation.
And this is kind of what blew my mind of the whole thing. Like, and I don't know if anyone caught this because he said it really fast. We're talking about FTIR gases.
Yeah.
Like we're not
That's
talking
exciting.
about FTIR like I'm putting a solid on a plate or a liquid on a plate. You're talking gases.
Yeah, and
that whole thing blew my mind. So,
and identification of gases. I mean, the gases are the dangerous ones, right? They're the ones that are going to come out and get you. That solid's going to stay there for a long time, but the gases is what presents some of the bigger hazards. And so we thought it was really important to come up with some technology so we could identify those.
And the two main meters that are encompassing that, they're the Threat ID and the Explorer IR.
Yeah. So the Threat ID
between those two.
So the Threat ID that's an interchangeable system. It can do solids, liquids, and gases, and you kind of change your interface between a standard ATR to a gas cell, right? So the ATR does solids and liquids, gas cell obviously does gases. But that's really kind of a system that sits in the warm zone, right? It's decountable, you can take it in, but it's pretty big. And so what most people do for gases is they collect it in like a Tedlar bag or a big syringe and bring it out and identify it there, which is a good technique. And it's nice because you have the combination, right? One instrument does two things. So it's kind of a nice thing. The Explorer is our more recent product. The Threat ID has been out for about 3 years. The Explorer we just came out with last year. And the really unique thing about that is it's to identify the gases where they are. Go on site into the hot zone with it, and it can constantly monitor and detect when there's a gas and then give you the identity of it right there where it is.
So it gives both the monitor and the detection.
Yeah. Yep. And both of the products for the gases, they have a library of about 5,600 compounds. So really wide range of compounds that you can do. That's the same. The limit of detection is about the same for both of them. So really it comes down to a usage model. Do you want the 2-for-1, or do you want to go in and do it directly where the gases are present?
I'm actually wrapping my head around this whole idea, because this was always the kind of metering, and I'm not saying RedWave, I'm saying FTIR in general is a outside the zone. We're trying to pin down exact things, and I got to say, RedWave is that just changed.
Well, yeah, and really it comes down to. What's the problem with trying to collect a gas sample? Well, I can't see it, right? Solids and liquids, right. I know where they are. I can pick them up. I can grab them. But the gases, you got to go fill that bag, and hopefully you got it at a place where there's good concentration. Hopefully there wasn't a wind current that took it away and stuff like that. Well, now if I can take that sensor right in and get some immediate feedback, then I can much more easily identify it. Okay,
so then my mindset is in traditional FTIR spectroscopy, right? I'm
right.
That's where my mindset, that's where I'm guaranteeing everybody that's listening to this is thinking about FTIRs are like that. But your Explore IR has to be using some different methodology in order to do this.
Yeah, we do. And, Here's a way to think of it is we all know with traditional FTIR, it says measure your background first, which is zeroing the sensor, right? And then measure your sample. And you do them back to back, background sensor, background sample, and so forth. With the gas, we can't do that, right? Because we're going to go look for it, right? I don't have a source of clean gas. So we had to change how that was done and be able to accommodate these big differences. So when I can do a background and sample, I can treat them 1-to-1. I just divide them. It's a ratio. The absorbance is a ratio. I just divide out my background and remove all that stuff there. But for gases on the Explorer, we had to take this in a more detailed approach. And we've got better computers, we've got better algorithms, all of this machine learning, big data sort of thing. Well, we can take some of those same things and apply it to the way we do it. So we break down that spectrum piece by piece, and we break down the water piece by piece and effectively remove that out adaptively. We use how much we need to use, right?
You make it sound like it's nothing. It's like it's so easy.
Do some of this, do some of this.
It took us about 2.5 years of R&D to do that. So that's where we had the thread ID. So we had all this data coming in for the thread ID, and then we were able to do the algorithms to figure out. But these are techniques that have been evolving over time, and we're bringing them to a product. But there's research that's been done on this sort of thing for a while.
So I can remember with the liquid solid type of samples in teaching guys how to use it. One of the things I would do on the sample was I would blow onto the diamond, and you could actually see the water curve or the CO2 curve. How does the machine pull all that out? I mean, if the older versions were sensitive enough to pick up my breath, how do you go about pulling everything out?
Well, I've got a couple of slides that kind of show this in a picture, and that kind of is like the best way to look at that. Could we pull those up here?
So what are we looking at?
What are we looking at here?
Yeah, so over on the left, this is 30 parts per million of ammonia, okay? And over on the left, what you can see is sort of the conventional processing, background sample, just like you would do. And we've got pointed out there with the red arrows, some water vapor, some CO2. That water vapor probably looks like what it looked like when you blew on the ATR system.
Yep.
When we use the adaptive atmospheric correction, we're able to model what those look like and pull it out. And so over there on the right, that's what the data actually looks like on the Explorer. Okay, after we've pulled that out. And all we see is those really sharp ones all the way over on the right-hand side. That's the ammonia. If we go to the next one, we can see how that compares to the library. So on the top, there's the library. Then the conventional comes down below. And then the Explorer is third. I also have on here what your score would be. So your score in the conventional is like 0.3. I still get ammonia as my top hit, but it's like a really low score. Right. But on the Explorer, I get a score of 0.92, and we're able to do a confidence value for that. So what we actually show you on the Explorer is a star rating, because it's nice and easy to see. It's easy to understand, 0.9 to 0.95, that's 4 stars, right? Pretty good. Right. 0.95 and above, 5 stars. That's good. It's as good as it's going to get. And so that kind of shows how we're able to take the water out of there and then give you a really nice usable way to grade that when you're viewing it downrange.
Is there a limit to how much water you can pull out? Like, is there a humidity? Like, you drop this off in New York in the middle of August, and it's 493% humidity.
We're in Connecticut. We're not much better.
Okay. But, you guys are like 360.
Yeah. So we've done testing, and we tried to do the most difficult way of testing it. So we collected what we're using for our background, and we collected what we're using at the sample. And on one side, we have 20% relative humidity. The other side, we had 85%, and we swapped those all vice versa. So we did high humidity sample, low humidity background, high humidity background, low humidity sample. We did 8 different compounds. We did 10 different concentrates. We ended up with like 4,000 combinations of this, wow. Right? And going all the way from 0 to 95% relative humidity, we were able, in saying that you're going to cut off at a response of 0.8. So 0.8 is your threshold. Anything better than 0.8, we report. Less than 0.8, we don't report. And our probability of identification was like 0.96 over that whole thing, right? So really, pretty much if you're not condensing water, and if you're condensing water,
so no rain. If it's not raining, then you're good to go. And just so the 0.96, we're not talking about less than 1% accuracy. We're talking about close to 100% in your hitting. Yeah. Yes. Okay.
Yeah. A probability of 96% that you're going to hit it right if you're in that whole range. And what we did is we started at 1 ppm as our lowest concentration. We went up to 300 ppm. So, some of those compounds, we just didn't see them because they're too weak, right? Infrared has some compounds absorb a lot, some compounds absorb a little, right? So we typically say that our limit of identification is in the low ppm. And what we mean is sort of 10, 20, 30 ppm. And we did a study when, I got to look at my statistics here, but we looked at 47 different gases, all which are on the OSHA highly toxic gases list. And of those, 72% we were less than 25 parts per million. And then 45%, we were less than 10 parts per million. And then the other 25%, we were, 25 to 100 parts per million. So, really, if you think about that 10, 25, you're sort of in the right range of where we'll be.
That's all right. Just a side note, because I'm trying to wrap my head around this thing. We're bringing the machine to the proximity. Are you guys now drafting through like a pump and a tube?
Yeah. We actively pump in. We have a gas cell inside, and it's interesting. The gas cell's like, I don't know, it's about this long. It's maybe 2 inches long, 2.5 inches long, but the path length of it is 2 meters, right? So it goes back and forth, 26 different times in there. So we get a lot of absorbance. We got a long path length to get a lot of absorbance, but a small volume. And we basically do a fill cycle of that cell every 6 seconds. So as you're going along, every 6 seconds, you're filling the cell. And then once we do a detection event, once we say, oh, I got something there, then we shut the pump off and we average the data, just like you do on the solids and liquids. You average the data. We average the data till we can get an identity. Then we show you the identity.
Now, if you're pulling out things like water, what about chemicals that are really close on the spectrum to water? Do you end up losing the ability to see?
Actually, I've got a picture of this as well. I've got the next slide there is sulfur dioxide. And this is an interesting one. Sulfur dioxide, this is 30 parts per million again. And on the left is your raw data, and in blue, and in red, that's where the library is. So that's completely under the water vapor, right? It is buried there. But after we do our adaptive atmospheric compensation, that's what we get over on the right. We nail it every time. Wow. And so the thing that you have to remember is we're looking at this picture here, but the data points there, that's not just one big block. There's individual data, and if we go through there specific enough, we can pull that information out of there and still be able to see that. So we're extremely confident of being able to see stuff, even if it's under the water vapor. The atmospheric chemists used to talk about this water vapor window, where water wasn't absorbing and you could see stuff without it. And with our technology, we don't have to worry about that. We don't make any compensation for that.
I got a quick question, and again, I'm just thinking about things as I'm listening to you. Is does polarity or solubility in the water have anything like, does it, because you're omitting the water? I mean, I'm sure at some point, some things that are like an alcohol that is immiscible, not immiscible.
Yeah. I get what you mean. Where we see that the most is like when you have a liquid and you're trying to measure the headspace, right? So we all know that like Windex has ammonia in there, right? The concentration of ammonia that comes off is really small because they put a bunch of surfactants in there to try and solubilize that ammonia, to try and hold it in solution so it doesn't come out. Now, it has nothing to do with the data. That has nothing to do with what we're doing to the data. It's just whether or not it's there in the gas phase. And a lot of times, this is the thing when people first try this, is they're like, well, I can smell that, but I couldn't detect it. And we all know our vapor threshold is all over the place depending on where it is. I mean, whatever the chemical that makes up skunk smell, our vapor threshold is really low for that. We can smell a tiny amount of that, right?
Right.
But the infrared also has its absorptivity. So sometimes you get into that sort of thing.
What about mixtures? I know typical FTIRs, they can do okay with limited mixture, mixtures in water or multiple materials. How does, when you start measuring gases in the atmosphere, how does that start to change, if it does at all?
Well, So one thing about gases is that they don't interact the same way liquids do. So if, like you had the example of an alcohol, if you take a liquid alcohol and you put that into water, they will hydrogen bond, and that'll slightly change the infrared bands. Because we all know that infrared bands are due to vibrations, and once you hydrogen bond them, you change that vibration.
Right.
Well, that doesn't happen in the gas phase. They're all separated, right? They're all apart from one another. That's what defines it as a gas. So in a way, the mixtures are easier. Now, right now, we're just finishing up the implementation of our mixture algorithm. So the version that people are using right now will tell you the primary component. Okay. But we are getting ready to release at the end of the year our mixture analysis capabilities. Everybody that currently has the Explorer will get upgraded to that.
Is that just software?
It's just software. It's just software that does that. Yep. And our initial results are really nice. I'm not quite ready to talk totally about it, but I can say that we are seeing better results than we see in solids and liquids, and better results than anybody is seeing in solids and liquids.
I will say that I know RedWave is a under promise and over deliver type company. So if you're saying I don't want to talk about it, it's like it's going to be pretty sizable.
It's coming. It's going to be good.
Yeah. Yeah.
Well, how does the company see themselves fitting into the response model of a hazardous materials technician, right? So I have your meter. I have a plethora of other meters. The general idea that we like to teach and talk about meters is this is a tool in the toolbox. How does it combine with other tools in the toolbox? How do I use it downrange? Where does it fit in? What is the language that it's speaking? How does it tell me what it's telling me, and how can I start to infer information based upon that? So where does this technology fit into the response model?
Well, so one thing to remember is just like all FTIRs and all Ramens, we're not intrinsically safe. So we got to make sure that we're in a safe atmosphere. Right. So
I mean, we're not intrinsically safe either. So
yeah,
that's why we try to stay away from LEL readings. So
yeah. So it's got to be behind, your basic threats. You have to, understand your LEL before you even think about bringing this in to detect. But the way I like to look at this is I cannot accurately assess a toxic threat without two things: identity and concentration. And so to assess the threat of a toxin, I have to know what it is, and that's what we provide. So it pairs with your other tools that it pairs really well with your other tools that are going to tell you the concentration of that toxin, such as the PID or the some of your electrochemical sensors. And if I can get the identity from the FTIR, then I make my PID reading a lot more useful because I can correct it, and I can understand what my response factor should be for that chemical. So I see the two of those going hand in hand. If a person's going, well, I got 700 on my PID. So what? What is it?
So what? Right. So what?
Right? There's something there, but I want to know what it is, and that's where we come in.
So do you ever see a point? I mean, listening to this and kind of playing with the meter a little in the past, do you ever see it almost taking the place of electrochemical sensors? Because in my mind, I've got all these electrochemical sensors out there. I'd have to bring in 3 or 4 different meters with all different electrochemical sensors just to get, or I could just take in one meter that has 5,000 essentially samples in it. Yeah, and I'm taking in 5,000 meters all at the same time. Is this a direction that you would like to see people start to think of this device, or are we just not there yet?
I'm sure our sales manager would love that, but
we have to remember. I'm lazy. right? I don't want to start up. No, I am. I don't want to start up 7 meters to walk down range. Like I would so much rather just grab 1 meter. So if we can get to the point where we're starting to just grab less and less because the technology is better than what we've been using before, do you see that moving in that direction?
I do, with a couple of caveats. And one of those is that I have a wide range of chemicals that we can identify. We can't identify all of them. And some of the specifics that it's just like solids and liquids, we can't do elements. Well, what's an important one? Chlorine, right? Cl2, we can't identify that in infrared, or bromine or fluorine, which you may run into in an industrial situation. And for those, your electrical chemical sensor is going to be your only hope. And then, there's other ones like H2S. We can identify H2S, but we're not very sensitive to it. So, your electrical chemical sensor is going to give you an oxygen. We don't identify oxygen. It's another elemental compound, right? So you still have to do those other ones to make sure you get all of them. But we're really, the way I see it is we're filling more of the gap where you wouldn't typically have an electrical chemical sensor for phosgene, or you might not have one for ammonia, or HCN. A lot of these industrial gases that are really nasty, but they have an important use in industry. A lot of those things then we're going to be able to identify.
Well, so like you mentioned ammonia, and real quick, just knowing what the blind spots are for ammonia with the meters that I have, my ammonia, my electrochemical sensor lets me know it's there in less than 50 parts per million, and then I got to put it away. I can't use it past that. My PID gives me readings, depending on your PID, up to like 10,000. So you talked about the lower end spectrum. Is there a high end limitation to the parts per million on the FTIR?
So our signal saturates just like any other sensor, right? And we have automatic detection for saturation. So we will alert the user that the signal has saturated. Interesting thing, though, is that it's only a data thing. So we don't affect the sensor at all. We don't affect the instrument. The instrument's still working fine. Our data is just saturated. So you back up into some clean air and let the pump dilute it, and then we can get an identity sort of on the backside. You imagine you go into a saturated situation, it goes straight up, and then you're saturated here, and then we pull it back out in the clean air. You come down on the backside, we can identify it on the backside. So typically, our saturation's going to happen above like 3,000, 4,000, 5,000 parts per million, depending on the chemical. But you pull it back and let it dilute itself, and then you can get an identity.
I gotta say, I am excited to get my hands on this thing and check it out. I'm hoping it'll be in the near future. I'm sure I'll see you at the conference circuit.
Oh yeah. We will be at quite a few this fall. Yeah.
Awesome. Well, I'm sure we're going to get questions of where we can see this, where they can contact you. So where would you send them to get the latest scoop?
So the website's kind of one-stop shop. They can go into the product side, go to Explorer, see that directly. They can get some more information about the technology, see some of our application notes, and our website is redwavetech.com, TECH.com, and that will that'll take you right there and get all the information that you need.
Doc, thank you so much for sitting down with us.
Well, thank you.
I think a lot of people are going to want to hear about this, so I have very confidence that this is going to be a very popular episode.
Great. Thank you.
Thank you.